In this video, we're going to talk about how to disprove statements. So we're going to talk about a few different kinds of statements, and we're going to show how to prove each of them. So first, let's consider a statement of the form for all x in S, P of x. Right, so this is saying for everything in S, P of x is true. Let's say we want to disprove it. Right, so until now, we've been talking about proving, how to prove that something is true. Disprove means to show that it is false. So how to disprove a statement of the form for all x in S, P of x. So let's think about it. Disproving it means to show that it is false. What does it mean to say that this is false? Well, the claim is that P of x applies to all the elements of S. In order to disprove it, what you'd have to do is show that there is an element of S such that P of x does not apply to it. And that would disprove the claim. So produce an element A, let's call it A, an element of S, an element A, such that P of A is false. And that disproves this statement, because the statement says that P of x applies to every element of S. And yet here we see an example of A that's an element of S, and yet P of A is false. Okay, so this is called a counterexample. This A is called a counterexample. It's an example that goes against the proposition, right? That counters the proposition and shows that it is false. So here's a little example. So here's a proposition. For every integer n, the number n squared minus n plus 11 is prime, right? If I do n squared minus n plus 11, that result is prime. Now this proposition actually works. Well, actually this formula actually works for many integers, right? Such as, if you try it out, if n equals -2 or 2 or 7 and many others, it will work. However, the proposition says that this applies to every integer n, right? So we have a statement of the form for all x in S. So the thing is, the proposition is actually false because it doesn't work in all cases. And here is a disproof of the proposition. So here's the counterexample. This is one of many different counterexamples we could give, but here's one. Consider what happens when n equals 11. What we have when n equals 11 is n squared minus n plus 11 is 11 squared minus 11 plus 11, which is 121, which is equal to 11 times 11, which is not prime, because, in other words, 121 is not a prime number, because in order to be prime, it would have to be only divisible by 1 and itself, but it's actually divisible by 11 as well. So therefore, 121 is not prime. So this shows that it is not the case that for every integer n, the number n squared minus n plus 11 is prime. Because here we have an example of an integer n where n squared minus n plus 11 is not prime. So this was a counterexample, and this disproves the proposition. Okay, great. How about a different kind of disproof? Disproof of a proposition that says, if P of x, then Q of x. So how to disprove a statement of the form, if P of x, then Q of x. So here's how we do it. So remember how we understand these kind of statements, right? Even though it doesn't say for all x, we understand these statements as having an implied for all x. So this is saying for all x, if P of x, then Q of x. So how do we disprove that? Well, we find an example where this part is true, and yet this part is false. Why? Because how do we disprove a conditional statement? How do we negate a conditional statement, right? What we want is the negation of the conditional statement, right? That's how we're going to disprove it. So how do we negate a conditional statement? Answer, we make this true and this false, right? So if we can find an example, A, such that P of A is true and yet Q of A is false, that disproves this statement. So for example, this is also called a counterexample, right? So this A is also called a counterexample. So here's a proposition. It says if A, B, and C are sets, so that's my if this, then this, then A minus B intersected with C is equal to A minus B intersected with A minus C, right? This is the claim is that that minus, that the symmetric, that minus, meaning difference, distributes over intersection. So that's what the proposition says, and we're going to disprove it. So here's a disproof. So here's the counterexample. Consider what happens when A is equal to the set 1, 2, 3, B is equal to the set 1, 2, and C is equal to the set 2, 3. So what do we have? So what is A minus B intersected with C? So B intersected with C is the intersection of this and this, which is just the set containing 2. So A minus B intersected with C is the set 1, 2, 3 minus the set just containing 2, which is the set 1, 3. On the other hand, we have what is A minus B intersect with A minus C. So that A minus B is just the set containing 3, right? A minus B. A minus C is just the set containing 1. So now we want the intersection of these two sets, which is the empty set. And this set, the set 1, 3, is not equal to the empty set. So, this has disproved the proposition. The proposition says that if this is true, then this has to be true. And yet here we found an example where we have where we have 3 sets, and yet the second part is not true. Okay, so we've disproved the statement of the form if P of X, then Q of X. Finally, last kind of disproof that I'm going to very briefly mention, but not even give an example of it. How do we disprove that something exists? Right. So let's say we have a statement that claims there exists an X and S such that P of X, that something exists such that P of X is true. So to disprove that, how do we do that? Well, what the claim is in this statement, the claim is that something exists. Something in S exists such that P of X is true. The negation of that would be that for all elements of S, P of X is false. That, in other words, P of X does not apply to every single element of S. So how are we going to show that? We're going to have to prove using direct proof or contrapositive proof or proof by contradiction that for all X in S, not P of X. And that will disprove the statement. Now for this, we can't just give an example, right? We're trying to show that for all X in S, not P of X. So, but the point is we're trying to show that this is the case for all X in S. So we can't just give an example. We'll have to use direct proof, contrapositive proof, or proof by contradiction. Okay, sorry, no example for this, but okay. It doesn't appear in the homework, at least if you're watching this in spring 2022. Something like this does not appear. This last one does not appear in the homework. So you can look in the book. The book has a nice example of this.